You dropped ice cubes into a drink this morning. Maybe you walked past a frozen puddle on the sidewalk. You didn't think anything of it. Why would you? Ice floats. It's always floated. It's one of the most boring facts in the world. Except it's not a fact. It's an anomaly. And if it weren't true, if water behaved like almost every other substance in existence, you would not be alive. Let me show you what I mean. Imagine a world where ice sinks. Winter comes. The surface of a lake freezes and the ice drops to the bottom. More water freezes. More ice sinks. By spring, your lake is a solid block from bottom to top. It never fully thaws. Ice at the bottom is insulated from the summer sun. Fish die. Ecosystems collapse. Oceans become frozen tombs. Nothing ever crawls onto land because there's nothing left alive in the water to crawl. That world almost happened. Nature is absurd and wonderful, but this time, the absurdity saved everything. A single molecular quirk, one angle of 104.5 degrees, stands between you and a frozen, lifeless Earth. And the strange part? It didn't have to be this way. Now, if you're like most people, you think you already understand why ice floats. You learned it somewhere. School, a documentary, a half-remembered conversation. Ice expands when it freezes, right? So it's less dense, so it floats. Done. Next question. But here's what that answer hides from you. Expansion is the anomaly. Almost nothing else does this. Think about it carefully. When you melt iron and drop solid iron into the liquid pool, the solid sinks. When you melt candle wax and drop a chunk of solid wax in, it sinks. Melt aluminum, mercury, sulfur, glass, rock, the solid sinks. This is the rule. This is what solids do. When matter solidifies, molecules pack closer together. Density increases. The solid drops. Ice breaks the rule in plain sight. Every glass of water, every frozen puddle, every ice-capped lake. The violation is constant, ubiquitous, obvious, and invisible because we've stopped seeing it. This bothers me. It has for years. Not because the physics is complicated, we'll get to that, but because I walk past this miracle every single day of my life without once feeling the strangeness of it. Common sense is just a collection of prejudices we acquired by age 18, and one of mine was that ice floating is boring. Unremarkable. Beneath curiosity. I was wrong. I want to show you what I found when I stopped ignoring it. Why does freezing make water expand instead of contract? What is special about the water molecule, specifically one angle, 104.5 degrees? That breaks the universal pattern. And why does this quirk matter so much that the entire history of complex life might depend on it? Hold that thought. We'll come back to what happens if that angle had been different. Where are you watching from? Drop your location in the comments. And if you've ever looked at ice and felt nothing, hit subscribe, because this is about to get much stranger. Let's find things out together. So let's start with what doesn't explain it. First answer people give me: air bubbles. Ice has air trapped inside. You can see it sometimes, those little white cloudy pockets in the center of an ice cube. Maybe that's why it floats. Less dense because it's full of tiny pockets of trapped air. This sounds reasonable. I've heard grown adults, smart people, scientists even, offer this as the explanation. But here's the problem. You can make ice with no air bubbles at all. Laboratory-grade ice, frozen slowly under controlled conditions, perfectly clear, not a single pocket of trapped gas. It still floats. The bubbles are not the answer. Cross that one off. Second attempt, temperature. Cold things rise, right? Like how hot air rises. Maybe cold water rises to the top and stays there as ice. This one gets the physics exactly backwards. Hot air rises because it's less dense than cold air. But in almost every substance, cold means denser. Cold iron is denser than hot iron. Cold glass is denser than hot glass. Cold air is denser than hot air. The pattern holds everywhere until we get to water. And here's a clue we'll need later. Water is densest at around 4 degrees Celsius. Not at freezing. Not at 0. At 4 degrees. Hold that thought. It will matter more than you expect. Third try. Maybe solids are just lighter than liquids. As a general rule, maybe I've been wrong about iron and wax and everything else. No, we've measured this. We've measured it for centuries, across thousands of substances in laboratories around the world. Solid iron is about 5% denser than liquid iron. Solid wax is denser than liquid wax. Solid nitrogen, solid oxygen, solid carbon dioxide, all denser than their liquid forms. This is the overwhelming default of matter. When things freeze, they get denser. Ice is the rebel. Ice is the exception. And exceptions, in science, demand explanations. So we're left with a puzzle. Ice floats. Not because of air bubbles. Not because of temperature directly. Not because solids are generally lighter. Then why? But anyway, I'm getting ahead of myself. Before I give you the answer, I want you to feel what's happening at the molecular level. Because physics makes no sense until you can picture it. Numbers and equations slide off the brain like water off glass. Images stick. So let me give you something to picture. Stay with me. Here's where it gets strange. Imagine a subway car at rush hour. Bodies packed in, shoulder to shoulder. No pattern, no order. Everyone filling every available gap. Maximum chaos. That's liquid water. Molecules bouncing, jostling, tumbling over each other, crammed into the smallest possible space because there's no structure forcing them apart. Pure disorder. Maximum density. Now imagine something changes. The doors close, a bell rings, and everyone is suddenly forced into a square dance. You must hold hands with specific partners. You must keep your arms extended at a fixed distance. You must maintain exact spacing in a geometric grid. Suddenly, the same number of people takes up more room. The structure itself creates space that wasn't there before. This is the beginning of understanding ice. But we're only peeling back the first layer of the onion. The real question, the deeper question, is what force makes the molecules dance? The water molecule is bent. This might sound like a trivial detail. It's not. It's everything. Oxygen sits in the middle. Two hydrogen atoms attach to it, but not at opposite ends, like a straight bar. They attach at an angle. A specific angle, 104.5 degrees. If you've never thought about molecular geometry before, don't worry. Neither had I, until I realized this single number might be the most important angle in the history of life on Earth. Here's why it matters. Because of that bend, the molecule has a lopsided electrical charge. The oxygen side is slightly negative. The hydrogen side is slightly positive. And positive attracts negative. This is basic electromagnetism. So when water molecules get close to each other, the hydrogen of one molecule reaches out toward the oxygen of another. This attraction is called a hydrogen bond. It's weaker than the bonds holding each molecule together, but it's strong enough to matter. In liquid water, these bonds are constantly forming and breaking. Jiggling atoms, constantly in motion. They link up, snap apart, link up again, millions of times per second. The chaos prevents any stable structure from forming. The molecules tumble freely, filling every gap, packing tight. Like that crowded subway car we imagined. No order, no pattern, maximum compression. But when the temperature drops, the jiggling slows. The thermal energy drains away degree by degree. And as the motion slows, the hydrogen bonds start to stick. They stop breaking so easily. They lock into place. And here's the kick. The angle forces a specific geometry. Hydrogen bonds can only form at certain angles relative to the molecule's bent shape. When they all lock in together, they don't pull the molecules closer. They hold them apart. The structure that forms is a hexagonal lattice, a repeating pattern of six-sided rings with empty space in the center of each ring. Remember the square dance? Now imagine something even more demanding. Imagine you have a pile of tent fabric collapsed on the ground. All the material is there, but it's compressed into a small heap. Now imagine you pitch the tent. You insert poles, pull the fabric taut, create rigid structure. Suddenly, that same fabric encloses a volume of empty space far larger than the material itself. The tent takes up more room than the collapsed pile, even though you haven't added a single thread. Ice is the pitched tent. Liquid water is the collapsed pile. The hydrogen bonds are the tent poles. When they lock into position, they force the molecules into a rigid geometric skeleton. And skeletons, think scaffolding on a construction site, are mostly empty space. That's what gives them strength. That's also what makes them light. Have you ever watched ice form slowly on a pond and wondered what's actually happening beneath the surface? Tell me in the comments. I'm curious how many people have stopped to think about this before. So ice floats because freezing doesn't compress water, it structures it. And the structure has mandatory gaps. The molecules aren't closer together in ice than in liquid. They're locked into a pattern that holds them apart. The scaffolding can't collapse. The empty space is built into the geometry itself. This is the opposite of what happens in almost every other substance. When iron freezes, molecules pack tighter. When wax solidifies, molecules get closer. But water is bent at 104.5 degrees, and that bend creates hydrogen bonds at angles that force empty space into existence. Nature doesn't care about your intuition. Ice is less dense than water because the rules of its molecular shape demand emptiness at the core. Hold on, because this next part should unsettle you. That 104.5 degrees isn't required by any fundamental law of the universe. It's a quirk of how oxygen and hydrogen happen to share electrons. The angle emerges from quantum mechanics, but it's not inevitable. It could have been different. In some sense, it almost was. Think of it like a lock that only turns at one precise angle. Insert the key at 103 degrees, nothing happens. Insert it at 106 degrees, nothing happens. But at exactly the right angle, the mechanism engages. The door opens. Life got the key. Let me show you what would have happened if we hadn't. This is where everything we've talked about becomes a matter of survival. Earth is 4.5 billion years old. For much of that time, life existed only in the oceans. Everything that ever crawled onto land, every amphibian, every reptile, every mammal, every ancestor of yours going back hundreds of millions of years, crawled out of water. If the oceans had frozen solid, nothing crawls anywhere. Life ends in the silence of ice. And the oceans almost froze solid. This is not poetry. This is geology. Remember what I said earlier. Water is densest at 4 degrees Celsius, not at 0. Here's where that becomes important. As winter chills a lake, the cold surface water sinks because it's denser than the warmer water below, but only until it reaches 4 degrees. Below that temperature, something strange reverses. The water approaching 0 degrees becomes less dense. It rises back to the surface. It freezes there at the top, and ice, even less dense still, floats on top of that. This creates an insulating lid. The ice shields the liquid water below from the freezing air above. Fish survive beneath it. Plankton persist. Microbes continue their slow chemistry in the cold darkness. Life continues, even through an ice age, because the floating ceiling of ice protects everything beneath. Now imagine the counterfactual. Imagine 104.5 degrees had been 180 degrees, a straight-line water molecule, no bend, no asymmetric charge, no hydrogen bonding in the same geometry, no hexagonal lattice with its mandatory gaps. Ice would form differently. It would be denser than water, like almost every other solid in existence. It would sink. Lakes would freeze from the bottom up. Each layer of ice would sink and be replaced by more liquid water at the surface, which would then freeze and sink in turn. By spring, solid ice from surface to mud. Insulated from the summer sun by the water above and the mud below, much of it would never melt. Each year, more ice accumulates. Ocean floors become ice tombs. The thermal circulation of the entire planet collapses. Earth becomes a white marble, frozen and sterile, orbiting a sun that cannot save it. This is not wild speculation. We have found evidence of snowball Earth, events in the geological record, periods hundreds of millions of years ago when ice extended from the poles nearly to the equator. Life survived those events, barely, in small refuges near volcanic vents and equatorial patches of open water. But those events happen with ice that floats. If ice sank, there might have been no refuges at all. The oceans would have become solid blocks of ice from top to bottom. Life would have ended before it ever left the water, before it ever built a spine, before it ever developed lungs, before it ever wondered about anything at all. One angle, 104.5 degrees. A quirk of quantum chemistry that didn't have to be this number. And that angle, that fragile, accidental, unremarkable angle, is why your great-great-great to the millionth grandmother survived long enough to swim, to crawl, to breathe, to wonder. This is what Feynman meant when he talked about the beauty hidden inside physics. Not pretty, not comfortable, beautiful in the way that a near miss is beautiful, terrifying at first, and then, once you realize you survived, awe-inducing. The lock only turns at one angle. Life got the key. Come back to the glass. Same glass you've held 1,000 times. Ice cubes floating at the surface, clinking softly against each other. Cold condensation sliding down the outside. You've picked up this glass without wonder. I know. So have I. For years, I was blind to what I was holding. But now you know what's happening. What you're looking at is not ordinary. It's a violation of how matter normally behaves, a molecular fluke that kept your ancestors alive through ice ages, that keeps fish breathing under frozen ponds right now as you watch this, that kept the oceans liquid long enough for something to crawl out of them and eventually build cities and invent glasses and put ice in them and wonder about ice. Remember the subway car, the square dance, the tent poles, the scaffolding? All of that is happening right now in your glass. The hexagonal lattice is there, invisible in the white clouds at the center of each cube. The hydrogen bonds are there, those tent poles locking molecules into a geometry that includes emptiness. The 104.5-degree angle is there, for billion years old, and still doing its quiet work. Here's what I want you to do. This week, before this feeling fades, before common sense papers over the strangeness again, go get a glass of ice water. Don't drink it right away. Just hold it. Feel the cold against your palm. Watch the ice float. Listen to the cubes clink. And let yourself feel what it actually is. Not boring. Not obvious. Not a fact you learned in school and filed away. A miracle of molecular architecture. A near miss with a frozen, lifeless planet. An accident of quantum chemistry that happens to be the exact accident that lets you exist. Feynman once said that knowledge only adds to the excitement and mystery and awe of a flower. He was right, but I think he undersold it. Knowledge doesn't just add beauty. It reveals the beauty that was always there, hidden beneath familiarity, buried under the prejudices of common sense. The ice floating in your glass was always extraordinary. You just couldn't see it. Now you can. If this shifted the way you see something as simple as ice, share it with someone who still thinks floating is boring. Subscribe if you want to keep peeling back layers of the onion with me. And tell me in the comments, what ordinary thing are you going to look at differently now? Thanks for staying until the end. The world is stranger than we let ourselves notice. Let's keep noticing.